Hi, today we will discuss force, work, and energy. These are fundamental concepts in structural engineering. First, we talk about Newton's law of motion. If you remember, first law of motion says a body will exist in a state of rest or in a state of uniform motion in a straight line unless there is force to change that state by forces imposed on it. This is the law of inertia. And we use this because if we sum up all the forces, it will be equal to zero. This is used for the equilibrium of forces. The second law states that the rate of change of momentum of a body is equal to the net applied force, which is the summation of all the forces is equal to its mass times acceleration. The second law of motion is the generalized equation of first law, because if there will be no acceleration, A is zero, then the summation of all the forces is equal to zero. The third law of motion is that in terms of the symmetry of forces, that is, for every action there is an equal and opposite reaction. This is very important in the analysis of structures, because as we analyze every structure, we need to apply this one. So the three laws of motion can be used in our structural analysis. But first, we need to know more about mass and gravity. What is mass? Mass is actually a measure of the amount of matter in an object. It is usually expressed as kilograms in SI or slug in this unit. Also, gravity or gravitation is a natural phenomenon by which all things with mass or energy are brought toward, or that is, gravitate toward one another. On Earth, gravity gives weight to physical objects, and normally the gravitational acceleration is expressed as meter per second squared in SI units, or feet per second squared in English units. So here, weight in science and engineering is described as the force acting on the object due to gravity. This is, in other words, the force exerted by a body as a result of gravity can be described as its weight. So from the Newton's second law of motion, that is, force is equal to mass times acceleration, or F is equal to m times A, for 1 Newton force is equivalent to the force to accelerate 1 kilogram at 1 meter per second square. So therefore, on Earth, the force exerted by a mass of 1 kilogram is 1 times g, that is 9.81 kilogram meter per second square. The kilogram meter per second square is also what we call Newton. So for 1 or 9.81 kilogram meter second square, equivalent to 1 Newton. Also, we need to know the magnitude of weight. It's very important that we have some feeling. We should feel the magnitude of the weight. Take note, the Newton is roughly the force exerted on Earth by an stationary apple. Also, since Newton is very small, we normally use kilonewton. Kilo means 1,000, so that's 1,000 of the Newton, or 1 kilonewton. For half of a kilonewton, that is equivalent to 50 kilograms. That is the weight of a whole bag of cement. In our case, that's 40 kilograms. But in Europe, we are using 50 kilogram bag of cement, which is about the limit for the average person to lift. So it's very light, or actually it's a small weight, 0.5 kilonewton. For a 10 kilonewton, there is about the total force exerted on the road by a small car, which is roughly a mass of 1 ton. Ton is 1,000 kilograms. So 1,000 kilogram is about 10 kilonewton. So at least you should feel that one. Zero point 0.1 kilonewton is about the weight of the cement. 1 kilonewton actually is almost 100 kilogram. That's my weight. So I can say 1 kilonewton, that's me. Or 10 kilonewton, that's the small car. Force, it can be push or pull. Force when applied to an object tends to change its motion or its shape, as you can see in the picture. In structural engineering, terms force and loads are used interchangeably. Force is a vector quantity, so it has both magnitude and direction. Load is a term frequently used in engineering to mean the force exerted on a surface or body. We have different types of load. Actually, there are five basic types of loads in structural engineering. That is tension, compression, shear, bending, and torsion. The tension versus compression. Force applied in the longitudinal axis of the member will tend to elongate. That is the tensile force. You have to apply a pull, or if you compress, push, that's the compressive force, and it will shorten the member. For the shear, bending, and torsion, force applied in the lateral axis will try to slice off the member, so that's shear force. Or one very simple example of shear force is when you apply a scissor. You have a paper and apply a scissor, that would slice off the paper. Okay. Also, we have bend the member. The bending will bend the member, or if you have a paper, it will bend the paper. But for the torsion, that's a different one. It's you have to twist the member. Just like marakag galaba after paglaban mo imo siyang pugaan. That's twisting moment or the torsional moment. Okay? So, lubagan mo siya. Bending, ibawag mo, shear, slice off. It's very important to understand these five types of forces because structural engineering will really focus on these five types of forces. To design structure, you need to consider these five. Of course, there are structures that's purely flexure plus shear, and there are also structures with torsion and bending, depending on the use of the structural member. Aside from the force, I hope that would be very clear by now. If we have a force or a load that will be applied to the structure on the surface or on a body. Aside from the force, there is what we call the concept of work. Work is when you do something. You work at your office or classroom. In your daily life, the things done by you is termed as work. But in physics, work is energy transferred by force. Work and energy are interdependent. So the definition of work in mechanics is this one. The work done by constant force of magnitude F on a point that moves a displacement S in a direction of the work of the force is the product of the force and the displacement S. So work is simply the force F times the displacement distance S. The unit for a work is 1 joule. 1 joule is force is Newton times the distance meter. So 1 joule is 1 Newton meter, or 1 J is equal to 1 M. The unit of work is joule, which is equal to 1 Newton meter. The energy is quite different from work, but as I have said earlier, the two terms are interdependent. Energy is the ability of a system to perform work, When you are sick and say that you don't feel energetic, that implies that you would not be able to do work. You don't have the sufficient energy required to perform work. On the other hand, when you are fit, you really feel energetic. Your body converts food into energy that is then stored in your system for use. Similarly, in mechanical systems, the energy is stored in various forms, which helps the system to perform work. For example, when an archer stretches the string of the bow, elastic potential energy is stored in the string. When the archer releases the string, the energy stored in the string performs work on the arrow, moving the projectile forward. So here you need to understand that there are two types of energy. If it is static, that is what we call the potential energy, and if it is moving, that is kinetic energy. From the static energy, if the object will move, this the static the potential energy will be converted to kinetic energy. So that's in terms of the velocity of the object. To understand the above terms by considering the following example related to structural engineering. If you consider a beam of length L, an axial tensile force P is applied at the free end of the beam as shown in the diagram. On application of the force, the beam elongates by a length delta. We have the original length L, by applying the force P at the free end, the beam elongates by a distance delta. Take note that the force is P in Newton. The work done by the force in elongating the bar is 0.5 P times delta. And the strain energy stored in the system due to this is work done on the system, which is equal to 0.5 P times delta. There's another energy in any structure. We call it the strain energy. Actually, strain energy is just the potential energy of the system. We just use a different name for it. We call it the strain energy. When external loads are applied on an elastic body, they deform. The work done is transformed into elastic strain energy U that is stored in the body. This energy is then utilized by the system, that is elastic body, to bring it back to its original configuration. This energy is also used by the system to keep the load applied on the body in a state of equilibrium. So if you remember in your mechanics of deformable bodies, you talk about the stress and strain diagram. So here is the stress and strain diagram for an elastic material. As you can see, as you apply the load slowly, and as you increase the loading, the stress will increase, so will the strain of the material. And if you plot it with the stress and strain, it will form a straight line. As long as the body forms into the straight line, and if you have to pull back, buuyan ninyo, the original length will go back. That is due to the strain energy of the material. The strain energy that is stored in the material. But if you have to go beyond the yield strength of the material, then the material will no longer go back to its original shape if you have to pull out. Buuyan na ninyo, dili na siya mabalik sa original niya. And that will no longer be elastic. It's beyond elastic. So we call it the plastic. So to understand this, by again considering the above example of an axial force applied to the bar, for the load P to remain in equilibrium, the bar has to generate an equal and opposite force P. The system in itself doesn't have any inherent energy to generate the required force. Hence, it deforms, that is, it will strain in the direction of the force. Thus, work is done by the force P in deforming the bar from its initial position to its final position. This work done is stored as elastic strain energy in the system, which then generates the required amount of force to counter the applied load. You can see In the figure, initially, bibira siya, then bibuyag, mabalik siya sa original blend. So in the figure, we could see that when the load is applied to the bar, there is no reaction from the bar to the applied volume. Only after it deforms, it is able to give the opposite reaction. The system will deform till it has generated enough strain energy to produce the force equal to the applied load. At this point, the system stops deformation and we say that the system has attained a state of equilibrium. What is the importance of all this in engineering, especially in structural engineering? The world we live in, to our understanding, is governed by the laws of physics. Proper understanding of these laws will help in better engineering judgment. When we start designing any system, we have to design in such a way so that the load transfer is efficient and the deformations are under control. The reason for this deformation of any system is that it has to generate the required amount of strain energy to resist the applied loads. Thus, by properly understanding the deformation behavior of the system, we could greatly enhance the efficiency of the design. These fundamental quantities also lay the foundation for various principles that we use to analyze and design structures. That's all. Thank you for listening.